Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we talk about an example where the data being analyzed has a normal distribution with assumed known variance sigma squared and unknown mean mu. The prior distribution that we will be using is also normal. Okay? Okay. So let's get to work. Let me show you the example that we're going to be solving together, that we're going to be working on together in this video. As you can see, the parameter of interest mu in this case represents the average length of 1-year-old rainbow trout. Okay, so mu represents that average length. Okay, we also have some information that suggests that length, right, this length has a normal distribution, and from that information we can assume, right, maybe they have a lot of records about this, and then we can assume that the standard deviation is 2 centimeters. Okay, so sigma equals 2. And then what we're going to have here is two experts, right, analyzing the data. We have Arnie and we have Barb. So Arnie decides to use a prior mean of 30 centimeters, and also as far as the variability goes, in his experience, right, in his opinion, that length we're interested in could be between 18 and 42 centimeters. Okay? Now, on the other hand, Barb doesn't know anything about trout, so she decides to be more flexible, right? And the prior that would reflect her knowledge or lack of knowledge, right, would be a flat prior. Okay? Well, in this particular case, the sample size that we have is 12, and after you do the math, right, in this case we don't have the raw data, we don't have those 12 observations, just a summary statistic, y bar, but we know that's all we need, right, that the sample of size 12, the information contained in that sample of size 12 is the same as the information contained in the sample mean, right? We are going to be concluding the same from the entire sample as we would if we just analyze the sample mean. So anyway, what we want to be doing in the end, the ultimate goal, is finding the posterior distributions. Okay, and to do that, we're going to be using those simple updating rules that we talked about in other videos, right? Remember that we have a couple of videos where we discuss those updating rules in detail. One of them is for a single observation, and then we saw that the updating rules for a single observation can easily be extended for a sample of size n. Okay, so let's go back to what we have here, and well, let's just translate the information that we have here. So parameter of interest, mu, right? Parameter mu, and it represents a mean, in this case an average or a mean length. Okay, so And we're going to be doing this for two experts. So we're going to have Arnie first. So each of them has a different prior. The likelihood will be the same, but the prior is different. So in this case, right, well, we have the assumption that sigma, or sigma squared, is known. So sigma equals 2, right? Sigma is 2. What else? What we have is that the prior mean, right, according to Arnie, is going to be 30 centimeters. So let's use m as usual to refer to the prior mean. So prior mean m is 30. Okay. And then we have that he doesn't believe that that length is going to be less than 18 centimeters and greater than 42 centimeters. Okay, so here what we have is that the prior standard deviation S is going to be 4. Let's try and make sense out of that number. So remember that according to the empirical rule, right? According to the empirical rule, the probability that a normal with mean, if x represents a normal with mean mu, well, let me use a different letter here. Let me just say mean, and here standard deviation. So what we have according to the empirical rule is that the probability that you have, well, the proportion of observations that you have between the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation that's 99.7%, right? 99.7% according to the empirical rule, right? So if we go back to the information that we have here, we have 42 and 18, okay? So 42 minus 18, right? So note that the difference, the distance between mean plus 3 times the standard deviation and mean minus 3 times the standard deviation is just 6 times the standard deviation, right? So what we have here, that 4 comes from that idea that, well, let's just do the math here. 42 minus 18, that's 24, right? So if you divide 24 by 6, that gives you the standard deviation, right? So that's where that number 4 comes from. Okay, that's why using that information that Arnie says, I don't think that that length is going to be less than 18 and greater than 42, right? We equate that distance between 42 and 18 to 6 times the standard deviation, right? Okay, so our prior standard deviation according to Arnie, S, remember that we use S for the prior. Okay, so we're good. What else? Let's see. That's, oh, right. What we have here is sample size of 12. Sample size 12 and y bar 32. So I think we have all the ingredients that we need. Remember, in the case of normal likelihoods, it's a better idea to use the updating rules than trying to use the generic formula for Bayes' theorem of posterior is proportional to prior times likelihood, because doing the math it takes a while and it could be a bit tricky. Okay, so let's use those updating rules. Okay, so we don't need this anymore, that argument. Okay, we have already said why the prior standard deviation is 4. Okay, so updating rules. Here we go. So remember that to apply the updating rules, we introduced the concept of precision, right? So the prior, the posterior precision will be given by the reciprocal of the variance, of the posterior variance. So remember that it is very easy to find the posterior precision. The posterior precision is given by prior precision plus sample precision, right? Now, something that you have to recall here is that y bar, given that we have observations coming from a normal, y bar has a normal distribution with mean mu, where mu represents the mean of a single observation, and the variance of y bar is just sigma squared divided by n, right? So let me just write that down here. So variance, let me write it down like this. Variance of y bar, that variable that we have here, is sigma squared divided by n. Okay? So, in this case, sigma squared is going to be 2 squared divided by n. So 2 squared, oh come on, well, that's good. So we have 4 divided by 12. 4 divided by 12, which in the end is going to be just 3, right? Well, 1 over 3. Okay, makes sense? So anyway, the thing is that in terms of the formula here, what you have to remember is that the precision is the reciprocal of the variance, and in this particular case the sample precision is just n divided by sigma squared. Okay? Well, so now let's do the math. So 1 over s squared, remember that s, prior standard deviation for Arni, is 4. So what we have is 1 over 4 squared and then what we have here is just 3, right? Makes sense? So what we have is 1 over 16 plus 3. But 3 is the same as 48 divided by 16, right? Let me just double check. So 48 divided by 16, that's 3. Nice. And this happens to be the same once we have a common denominator. This happens to be the same as 49 divided by 16. Okay, so bottom line, our posterior precision is just 49 divided by 16. Okay, so remember that we do this because we want to find the parameters of our posterior. We know that the posterior distribution has a normal distribution, right? So recall that posterior distribution is normal with mean m star. That's the way that that's the notation that we use for the posterior mean, and variance s star squared, right? That's the notation that we use. Okay. So what we have here is that, well, the posterior variance is just going to be 16 divided by 49. Okay? Okay. Now, next, we need the other parameter, right? We need the posterior mean, m star. So what we know about m star is that m star will be a linear combination of our prior mean and our posterior. I'm sorry, that our posterior mean will be a linear combination of prior mean and sample mean. Okay, and those multipliers, those coefficients for each of those components for the prior mean and the sample mean are like this, right? We know that here, if m represents the prior mean, what you're going to have is this: 1 over s squared, right? Meaning the prior precision divided by the posterior precision, which is this guy. And then for the other one, right, the other component is going to be the sample precision, which is n divided by sigma squared, times the sample mean, which is y bar. Now you will see something interesting here, and we mentioned that in our video when we talked about these updating rules. Note that the sum of these guys is 1, right? Okay, so let's see. So note that this guy, 1 over s squared, is this 1 over 16. Oops, 1 over 16 divided by the posterior precision is this 49 over 16, right? Times m, the prior mean according to Arnie was 30. So we have 30 here. And then note that n over sigma squared, that's this guy here, and the posterior precision is this. And sample mean y bar was 32, if I remember correctly. Yeah, it's here. From this we can easily see that, oh yeah, these guys cancel out those numbers, 16 and 16. So we have 1 over 49 for the first one times 30 and then we have 48 over 49 times 32. So in the end, once we do the math, we'll have the value of the posterior mean m star. Let's do it, right? 30 over 49. Well, we could do it like this, right? It's going to be 30 plus 30 plus 48 times 32, both of them divided by 49. So that's our value for m star. Okay, so bottom line, our posterior distribution, or Arnie anyway, is going to be normal with mean m star 31.95 roughly, and a posterior variance of 16 divided by 49. 16 divided by 49 happens to be roughly 0.3265. Okay, so we're done with Arnie's posterior distribution. We just applied our updating rules. It wasn't that hard. We just had to be careful, and that's it. Now let's just finish the one for Barb. Okay, let's do the one for Barb. So Barb used a flat prior. Okay. So what we know about that flat prior, and we talked about flat priors in another video, what we said is that flat priors are going to be assigning a constant value to any of the possible values for mu between negative infinity and infinity. What we said about flat priors is that they are improper priors, but even though they are not legit prior distributions, once we apply Bayes' theorem, it works fine. And we also said that for flat priors, our updating rules also work well. So let's just remember how that goes for flat priors. So the we need the precisions, right? So let me just copy paste what we have here about posterior precision. So let me copy paste that formula, and then I'm going to be modifying that accordingly. So for barb, we have a flat prior. So what we said is flat priors have an infinite variance, which means that the precision for those guys is 0, right? So our prior precision is 0. So the only one that matters is the one for the sample, right? And in the case of our sample, we have 12 observations, remember, and sigma squared is 4, right? So what we end up with here would be just right? So it would be just n equals 12. This would be 2 squared, right? So we have 3. Make sense? Okay. Which means that our posterior variance will be just 1 over 3. Make sense? Over 3. Then what we said about the posterior mean. M star. So we said that the mean for a flat prior is not well defined. It could be anything, but what we know is that the posterior mean is a linear combination of our prior mean and our sample mean, y bar. Okay? So let me copy paste that formula. Note that the prior precision is 0, right? So we have 0 here times your prior mean, but your prior mean could be anything. So, but we have 0 times this, that's going to be 0. Then we have your sample precision divided by your posterior precision, which happens to be this, right? So since you have the same here, this simplifies to y bar. So bottom line, the posterior precision, the posterior distribution, right? The posterior distribution for barb is normal, mean m star, which is y bar, and y bar, if I remember correctly, is just 32, right? 32, and we said that the posterior variance is going to be just 1/3. Make sense? So that's it. We're done. Okay, so just to summarize, what we did here is we considered two different priors to analyze data from a normal likelihood, right? The prior that we considered first was a normal prior with the assumption that the variance was known, and for the likelihood, and the other one that we considered here is a flat prior. And again, to deal with this kind of a problem from a Bayesian perspective, it makes more sense, it's faster to do this using those updating rules, okay, to find the posterior mean and the posterior variance of your normal, okay, which happens to be the posterior distribution in this case. Well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.